things more confusing. Okay, excellent. So let's try another one here. We'll do just a few of these. How about, so practice again. Let's take this alcohol now, and let's turn this into this compound here. So this would be fun in our classroom, because normally I would have people work together in groups and share answers and solve the puzzle here. But we'll try to recreate that here as we all sit in our little Zoom boxes. And so let's turn that alcohol into another alcohol. So now notice number of carbons. Yes, there is a difference. Looks like we added a couple carbons. 2, functional groups, no change. So it's an OH to an OH. And 3, the location, no. The alcohol is in the same spot. So now we need to think about a way to add 2 carbons. And you can do this, you can use any reagent you want, as long as carbon only has no more than 4 bonds to it. And so any reagent you want, and you can do it as many steps as you want, but I would suggest probably two steps. So I'll pause for a minute and let everyone have a chance to think about it. So hopefully everyone's coming up with something. A little bit better. So we want to add 2 carbons. So probably a good way to do that would be to use a Grignard reagent. What if we had this ethyl magnesium bromide? We know that that could add to that aldehyde here. So this is going to nucleophilically attack here, move these electrons up onto this oxygen, and then we could protonate that with acid. So that would actually give us the product we want. In terms of both the alcohol, I'm ignoring stereochemistry here. Yeah, we get the alcohol, plus we've added our 2 extra carbons. So that seems great. Now all we need to do is convert our starting primary alcohol to an aldehyde. And for that one, we know that we have oxidizing agents that we could use. And now we need to make the right choice, though, because it's a primary alcohol. We want to stop at the aldehyde, so we can use PCC and dichloromethane, not chromic acid, because that would give us the carboxylic acid. Okay? So hopefully we're seeing the pattern here that's coming up. So I think just 2 more here. Any questions about that one before I scroll up? No? Is this fun? Yeah. Everyone says maybe. Yep. Okay. I'll take that. It'd be all. Okay. Yeah. Hey, excellent. That's fantastic. So we'll do 20 more then rather than 2 more since it's fun. Now we'll do what I wanted to show. Sorry, for this one here is let's just bring in a bit of this working backwards with this one, and because I know when we first presented, it seems like that seems overly complicated, but there is a reason for doing this. So retrosynthetically, what we would end up doing here, the retrosynthesis is really most useful when you're making carbon bonds. And that's the key thing in a lot of organic synthesis. And I think maybe I mentioned this the other day, is that what we're doing now, and this is the first example we've seen the synthesis up at the top, is we're making a smaller compound larger. So in this case, we're only adding 2 carbons, but imagine this was a really big piece that was being added. So that's really important in organic chemistry. If we want to make Taxol or Lipitor, we're generally starting with something smaller and making it larger. So what we end up doing when thinking about this backwards or retrosynthetically is we want to think about where can we form a carbon-carbon bond. That's the key thing. And retrosynthetically, you want to think about, so where can I disconnect it? And so if I'm going to form a carbon-carbon bond, when I'm thinking backwards, we're going to end up breaking this bond here with the red squiggle. And that's where the retrosynthesis helps, is that the terminology is I could disconnect, or I could break apart between here and here on paper, which means though in the lab, actually, I could form a carbon-carbon bond at this position. That's the key thing. So you start thinking going backwards with our retrosynthetic arrow, is that if I had this compound here, I know I would need to have an aldehyde, plus if I had something like this Grignard reagent, I know I could take these 2 species to get this compound that I want here. So I'm mentally breaking this bond, making this compound into smaller compounds. And then we could go back even further. If our starting material is that alcohol, I know that I can make that aldehyde from an alcohol, for example. So what you want to do with this retrosynthesis or retrosynthetic analysis approach is you want to find what are known as the disconnection points. Disconnection points. I think that's a real word as well. And these are typically things like a double bond or a triple bond, a ring junction where 2 rings might come together, next to a heteroatom, such as oxygen, nitrogen, sulfur, so on, and then next to a functional group, or part of a functional group. All right, okay, not sure that's capitalized. Okay, I guess we'll stay as it is. So as an example here, and I don't expect us also to memorize all of this sort of stuff, but just to start thinking about how we might apply this. Let's use this compound. Let's make this benzene. So we're starting with this compound here, which actually happens to be styrene. And we want to turn this into this compound. Okay, so that's our synthesis. We want to start with this one, and then this is going to be our final product. Now, in terms of our questions, have we changed the number of carbons? Here, we have, yes. So we've gone from, it looks like we've added an extra carbon at this position. Have we changed the functional group? Yes. Looks like we've gone from an alkene to an alcohol. 3, have we changed the location? And here, it's really kind of like, I don't know, say no, because we have, it looks like it's still in the same part of the compound. We could say it's either really yes or no. So in order to do something like this reaction, to help organize the thinking, this is a case where one might want to work backwards. So let's make sure that that stays the same. So retrosynthetically, let's draw our final product. And we want to think about a disconnection. I don't think we need the word make then. How about just say disconnection? We want to think about where can we actually break a carbon-carbon bond that would then, in the forward direction, is where we could make one. And dealing with compounds that are alcohols, where we're adding a carbon, a Grignard or an organolithium or something like that, seems like a really good approach for that. So what we would do is we'd look at this compound and say, okay, here's our functional group, a hydroxyl here. That's maybe where I could use some sort of a reaction to introduce a methyl group. Because here I just have the one methylene here of the double bond of the alkene. I need to add an extra methyl group. I'm not going to add a methyl group over here in the benzene ring, but it's here where I have the alcohol. So what I should do is break off this bond here, and then that should be able to give me my final product. So then when thinking backwards, think, how could I actually do that? How could I break that into two starting materials? Well, if I had everything here is the same, what if I just had a ketone? That seems reasonable. And then what if I added, I'll write CH3 so it's easier to see, methyl magnesium bromide. So if I had those two compounds, that would allow me to make my final product that I wanted. And then you start thinking, well, okay, that's fine, that's that ketone, but that's not really what I have as a starting material. I need an alkene. So I could now do some functional group changes. So now what I'm going to do is change that backwards, that ketone, the carbonyl group, into a hydroxyl group. And may not have really discussed these reduction reactions much yet. It depends on the order that you went through in 220A. We'll see these again, but let's just say we can do that. And then last, we could carry out an elimination reaction. Now we're in familiar territory, where I could turn that back into this species here. So that's thinking about this backwards now, but then in terms of the actual synthesis, what we would end up doing is then turn it around. Say, okay, I have my starting material like this. Now, what I could do is maybe I could add either water and acid, or you could use the hydroxymercuration reaction if you had talked about that. It's going to add water in the more substituted position. And then here, actually earlier I misspoke when I said reduction, because I was doing what you're not supposed to do, not thinking about the reagents. We want to go in this direction now in terms of the actual reagents, and so I probably made it more confusing. What we want to do is to reiterate here in reverse, is we're thinking about, I could make this ketone from an alcohol. So we're just conceptually thinking about that. So please ignore what I said about reduction. That's not relevant here. That's my mistake. What we want to think about is, if I have this ketone, what could I make this ketone from? And I could make it from an alcohol. So now when we're going in the forward direction, we know, okay, I could use, we'll just say PCC because it's shorter to write. Doesn't matter in this case because it's a secondary alcohol. That's going to make my ketone. And then last, I'm going to do my Grignard reaction. So using ether as the solvent. And I did not save enough space here. Give me my final product. Okay, so this gets to be a little bit more challenging.